Hello. So this is a presentation on spectral measures. It's the sixth and the last one from the series on operator algebras. So the idea will see to try to see how this probability business can help in relation with all these quantum algebra problems. So let's find this presentation. So spectral measures and beyonds. That would be the idea, to look at spectral measures and then to get to more advanced mathematics in this way. So I recall from the last time, or even if you don't know, there are basically four types of quantum algebra beasts: quantum groups, tensor categories, planar algebras, factors. Quantum groups, the basic examples are the compact quantum groups, Alavoronovich. Tensor categories, in this case, these are just the home spaces. Planar algebras, it's a part of the tensor category, just the n spaces. And subfactors, once again, in this very simple setting, these are the subfactors implementing this planar algebra. And well, in all this, it's these four types of objects don't really, overlap, but none is really more general than the other. But somehow the main problem in all this is to classify the finite index of factor, the hyperfinite factor R of Murray von Neumann. At least that's my opinion. Now you can go in many senses. These were the very basic things. So we'll need here some further beasts to go in this sense. So you can also restrict attention to the quantum permutation groups, tensor categories as before, but this time you consider the fixed points. So these are so-called speed planar algebras and correspond to this kind of fixed points of factors. Of course, you can extend these things to, everything is based on the permutation group, which is permutations of one, and you can use an arbitrary finite non-commutative space instead. So only these two things. Now, let's define an analytic invariant. We need invariants for all this, and the good invariant is the spectral measure. So for the quantum group, it's just the law of the character. For a planar algebra, is the measure having as moments the dimensions. It's the same thing by Peter Weil in these very simple examples. And as a comment, well, this invariant is not that known. Especially algebraists, they don't quite, they're a bit afraid of probability, but they use the Poincare series. And this is just the Stilbert transform of the spectral measure. So it's basically the same thing, but it's better to do it with measure because you get into probability. And there's a lot of source of inspiration there. These guys know what they're doing, the probabilists. So let's see precisely what they're doing. So we'll need classical and free probability at the same time. So you have here the definition of independence, freeness of Voiculescu. The basic examples are group algebras are independent inside their tensor product and free inside their free product. And with this, we have good models here. You can find transforms which linearize the usual and free convolution. These are log Fourier, very classical, and the R transform of Voiculescu. Now, as you have this, you can start proving limiting theorems. So this is the CLT first. Goes to the normal law, of course, you all know this. In the free case now, when the variables are free, exactly same assumptions as before, you get the Wigner semicircle law. So this is very interesting. That's Wigner found this in connection with physics random matrices. So it's a very interesting thing. Now, the other couple of theorems are the Poisson and free Poisson. So Poisson, you all know, you get is Bernoulli convolves, and you get Poisson laws. In the free case, so if you take the same Bernoullis but now free convolution, you get a Marchi-Pasture law, which is once again discovered in the context of random matrices we shared this time. So very interesting free Poisson convergence. Now, one more step, and we're done with the basics. You can do more generally compound free Poisson laws. So you replace delta 1 by an arbitrary measure here, rho, with respect to the Poisson limiting theorems. And the important examples here are when rho is the uniform measure on the roots of unity. The output measures are called classical and free Bessel, and will be interesting, especially in the cases S is 2, where we get real measures, we'll call them real Bessel. And in S is infinity, when you have the uniform measure on the whole unit circle, these are called pure complex. So now knowing all this stuff, let's go back to the core objects. So the quantum groups and planar algebras and all that. So I'll consider just these objects here, the those that we know, I mean, already when you enter free analogs, and also the hyperoctahedral group, the complex reflection group, and their free analogs. In planar algebra terms, well, on the bottom it's well known, and on top it's always temporally Libfus-Catalan depending on the correspondence which is chosen. Now let's compute for these A objects the measures, and the point is that you get exactly this laws in free probability: Gaussian, complex Gaussian, linear, semicircular, plus circular, and then all these Bessel things for reflections. And importantly, the computation in the quantum group case work for truncated characters. So you can add the truncation parameter there when you take the trace, just stop at t. And so you get actually t versions of all these measures as appearing in the previous slides. It's important because in free probability, the liberation by ejection between classical and free measures is actually between semi-groups of measure depending on a t. So that's the good statement. The quantum group statement is the best because you have this parameter t. Now, how can we go beyond? So these were very, very basic things. I mean, going back to, I don't know, 10, 15 years ago, even 20. So there are many problems in quantum groups. These kind of quantum groups, the 8 of them that we've seen are easy. And that's something I won't explain here. But that's somehow the simplest class of quantum groups. And the problem is to classify them and go beyond. Also, there are many problems more advanced regarding random determinants and advanced probability a la Diaconis. Now, in subfactors, all this was concerning temporally Libfus-Catalan, but there are many, many interesting problems, for instance, Poincare series obstructions of von Jones to understand how they, what's their probabilistic meaning, and also gel the spectral measure to do blow up for it, to blow it up on suitable manifolds. That's things I did a bit with Dietmar Bisch and then Ivan Sempiu. I did a lot of work on this. Also to understand what is T. I mean, in quantum groups we have a T in subfactors. We already have a T, and also to understand what's a big index subfactor independently of quantum group. That would be very interesting because all these things are easy somehow. They depend on n, which is continuous. So what's a big index subfactor? And finally, free probability and non-commutative geometry. The problem is that these 8 objects we're talking about are somehow the basic quantum groups in non-commutative geometry, but they're also the tori, and the tori were missing there in our diagram. And these are the liberation of tori. Actually, it's not Berkovich-Pata, it's Meixner-free Meixner correspondence. So that's a joint problem somehow free probability RNCG to unify Meixner and Berkovich-Pata. So we have here, you see, when we try to go beyond all these things, which are very old, you have quantum groups of factors, free probability, and non-commutative geometry are related. So as a conclusion, that's the picture of modern operator algebra. So the hot areas are exactly here: quantum group, non-commutative geometry, factors, free probability, physics probably in the middle. And here you have the precursors of system algebra for Neumann random matrices and E groups. So that's somehow it's all about the whole stuff here. And yeah, many, many things to be done. Okay, so I hope that you like it. And of course, if you're interested in these things, there are books, blogs, everything, and also presentations here at my channel on these separate topics, which are more bigger slides and longer presentations, running from 20 minutes to up to 1 hour. So you have everything on internet if you're interested in all this. Okay, so bye-bye.